So today's lesson is going to be an extension and continuation of our gas laws. Let's talk about gases. Gases are what we call a real gas. And what does that mean? They are subject to intermolecular forces, where that simply means an attraction between particles. And we're going to dive into the concept of intermolecular forces on a different video. All right, but for the purposes of this video, they are simply an attraction between particles. Real gases are able to liquefy under extreme pressure. For example, a propane tank, if you have a gas grill, and you have ever filled your gas grill, that propane tank. All right, when you fill that up and you're carrying it, it may sound like liquid is sloshing around in the tank. And that's because that is a liquid. That propane is under such an extreme amount of pressure in that tank that it has liquefied. Now, when you turn on the gas grill and that propane leaves the tank and goes into the grill, the pressure is going to change and it will go back into its gaseous form. All right, so we have a decrease in pressure and it goes back into its gaseous form. Real gases have volume. And we say under the following conditions, a gas is a real gas: high pressure and low temperature. Under high pressure, particles are super close together. All right, because remember, a high pressure is a low volume. An increase in pressure is a decrease in volume. So if I push particles really close together, then they are more subject to these attractions. Low temperature. Remember, temperature is the measure of average kinetic energy. So if particles are moving real slowly, then they are more likely to interact and stay around each other and then again be subject to these attractive forces. The reality is gases typically do not behave as a real gas. And in fact, they behave as what we call an ideal gas. Gases behave under the following conditions as an ideal gas: low pressure, high temperature. Remember, a low pressure is an increase in volume. So the smaller the pressure, the larger the volume. The larger the volume, the more space for those particles to be. All right, and the less likely they are to be hanging out around each other and therefore interacting and subject to attractive forces. High temperature. Rapid random motion is happening at a high temperature because they have a high kinetic energy. They are zooming past one another quickly enough that there is no, or the ability to attract one another is decreased, okay? Kind of like when you're running to class and you're on your way and you're late, all right? And you're running to get there real quick. You may pass a friend in the hall and you just say, hey, bye, and you keep going. You don't have time to stop and chat with them because you don't want to be late. All right, we can assume that gases are going to behave as ideal gases under the assumptions of what we call the kinetic molecular theory, where gases are tiny particles that are far apart from one another. They have a constant and random motion. Their collisions are elastic. All right, so we assume when they collide, there is no loss of energy. It is a complete transfer of energy. We assume they have no intermolecular forces. All right, there's no attractions between those particles. And we also say that kinetic energy will depend on the temperature. All right, so kinetic energy is depending on temperature. And that makes sense because temperature is the measure of the average kinetic energy. Now, when we have our ideal gases, we can use the ideal gas law, where PV equals nRT T. P is my pressure. V is my volume. N is my moles of gas. R is my rate constant. And T is my temperature. And again, temperature is going to be in Kelvin. So my R is going to be found on our chemistry reference tables, and you should have a copy of this so you can see it better. Let me zoom in a little bit here. We have 3 different R values. Notice that all of my R values have liters, so my volume is going to be in liters. All right, my volume is going to be in liters. We have mole of gas, all right, mole of gas in a mole. We have K for our temperature in Kelvin. So what is the only difference here? ATM for atmosphere, millimeters of mercury, and kilopascals. So this value that we use on our R is going to be dependent on what pressure you have. So you need to be very careful when you are solving these problems so that you are solving with the correct R value. So here we go. My pressure is going to be dependent on what I have in the problem, and I have to match my unit of pressure to my correct R value. So let's do some practice examples. If I have an unknown quantity of gas at a pressure of 2.4 atmospheres and a volume of 25 liters, a temperature of 80 degrees Celsius, how many moles of gas do I have? So my formula is PV equals nRT, where P is my pressure. In this case, that is 2.4 atmospheres. My volume is 25 liters. Volume has to be in liters, so this is already in liters. I don't have to change it. Equals N, that's what I'm looking for, how many moles of gas. Now, what R value am I going to use? My pressure is in atmospheres, so I'm going to choose my R value with the atmosphere, which is 0.0821. Liters per atmosphere over Kelvin mole. And my temperature has to be in Kelvin because my R is in Kelvin. So I'm going to convert 80 degrees into Kelvin, and that is 353 Kelvin. So now I could just plug this into my calculator and solve. And when I plug this into my calculator and solve, I find that N is going to equal 2.1 moles. All right, number 2. If I have 10 moles of gas at a temperature of 52 degrees Celsius and a volume of 71.4 liters, what is the pressure of gas in millimeters of mercury? So I'm solving for pressure. So P is what I'm solving for. V for volume is going to be 71.4 liters equals N, my moles of gas, which is 10. R. Now I'm asked to solve for pressure in millimeters of mercury, so I need to get the correct R value that will give me the unit millimeters of mercury, which is 62.4. Liters per millimeter mercury over Kelvin mole. And my temperature is 52 degrees Celsius, so that is going to be 325 Kelvin. All right, so now when I plug this in and I solve, I'm going to end up with a pressure of 2840 millimeters of mercury. All right, number 3. How many grams of argon would it take to fill a light bulb with a volume of 47.5 milliliters at STP? So this problem is going to be a multi-step process. All right. I have a standard temperature and pressure. We can use standard pressure in atmosphere, millimeters of mercury, or kilopascal. I'm going to choose to use kilopascal so that we can also use this final R value. All right, so we have 101.325 kilopascals. Remember, that is our standard pressure in kilopascals. My volume is 475 milliliters. Now remember, my volume needs to be in liters, so I have to convert milliliters into liters, so that's 0.475 liters, equals how many grams? So I'm going to first solve for moles of gas, and then from there I'm going to convert it into grams. I'm going to use my correct R value that matches my kilopascals, which is 8.314. And my temperature here is at standard temperature. So standard temperature is 273 Kelvin. So first of all, I have to find my moles. So when I plug this into my calculator and solve, I find that my moles of gas is 0.0212, and the gas that I am specifically using here is argon.